My name is Subith Vasu, and I'm a professor here. Today I'm going to talk about the experiments that we are doing that address ongoing urgent needs in the federal government and in the world related to zero carbon electricity generation, high-speed vehicles and propulsion concepts. And when it comes to space exploration, it's low cost and efficient techniques and technologies for space exploration. So a little bit for the typical faculty talks, we are asked to provide this about our background and accomplishments. So been at UCF since 2012, and before that I was at San Diego and Stanford. Then I got my undergraduate degree from India, IIT Madras, and I also spent a year at Politecnico Milano. So I've been educated in 3 continents, Asia, Europe, and North America. At the UCF, I taught 8 different classroom-based classes, several of them undergraduate courses and some graduate level classes. And here are some of the achievements from our group. So we do publish a lot. So we have around 110 journal papers from my group, and close to 250 conference papers, and actually more than 80 of the journal papers have been co-authored by my students. And I've been also fortunate to get some of the early career awards. The most notable one from the DARPA Directors Fellowship. So it's DARPA first awards the Young Faculty Award. Around 30 professors from all fields get it in the US, and then based on the performance and the importance of the project, they select a few out of those to the Directors Fellowship. That's the highest award within DARPA. So I've been fortunate to get that, and a few other things here. Currently, I'm on the International Energy Agency task team, representing the US, looking at energy solutions for the future. So we have meetings a few times a year, and so on. So moving on to the motivation behind our research. So my training is in aerospace engineering, mechanical engineering, and spectroscopy, optics, chemistry, and it's kind of a confluence of all those, which allows me to address problems in different areas. Most of the common theme behind all these areas is the high temperature reacting environment. So if you look at like a gas turbine, which generates power, you burn fuel and produce electricity. When you look at airplanes, you have engines that produce propulsive power. And when you look at cars or trucks, same thing, right? You're burning fuel, and those are like high temperature environments. When it comes to forest fires, explosions, it's the same thing. You have something that is burning and producing that high temperature environment. Same thing for the rockets and the high speed weapons and flights, supersonic flights and hypersonic flights. When you look at power generation, it's again a high temperature environment that produces electricity, but also a lot of unwanted pollutants. So when it comes to power generation, the key things going forward are trying to minimize the carbon footprint, decarbonize, reduce CO2 emissions, reduce pollutants. When it comes to high-speed propulsion, the key things are performance, right? That's the most important one. How can you fly faster, longer, and higher? It's still the motive. When it comes to space exploration, it's cost is the major thing right now. That apart from NASA, Blue Origin, SpaceX, and there are other hundreds of companies trying to build their own launch solutions. And so these are the main areas that we work on. And also we do a lot of field measurements. So we make laser-based sensors, and we take them to a field event. It can be an engine experiment, it can be an experiment in a DoD facility or a industry facility. And so we use this to measure the flow parameters in a high temperature environment. Typically, in order to do those kind of plug and play kind of measurements, we have to develop these kind of techniques. And so we work on developing those techniques. And just developing is not enough. You have to actually characterize them in a relevant environment. So we use facilities, some of them world-class facilities at UCF that we built to do that. And eventually, when you do this kind of field measurements, you produce information like here is the temperature, here's the species that are present in that high temperature environment. So these are the facilities that we have. We have multiple shock tubes. So this is one of the shock tubes, and this is a new shock tube called Hyperstar. This is a unique facility in the world. There's no other country has such a facility. This can access a variety of high pressure and high speed environments that are applicable to industry and the government programs. We all, here are some examples of laser measurements that we have done, and here are some other facilities that we have. So basically, we use these sensors and tools to look at the high temperature reacting environment. In terms of sponsorship, I've been also fortunate to get funding from a variety of agencies, from federal. So right now we have ongoing projects from NASA, DARPA, NSF, DOE, FAA, DITRA, JSTO, Army, Air Force, ONR, and so on, and several industries that fund our research. Obviously, I cannot talk about every project that we have, so I'll talk about a few new and ongoing projects in the area of each of these areas that I mentioned. So let's first look at what's happening in the transportation and electricity generation sector, right? So this is one of our new projects. So it just got awarded from DOE, and here's the DOE press release. And what the Secretary of Energy, Jennifer Granholm, talked about this project is that we need our, so when it comes to hydrogen power, it's not just the US that is saying that let's create hydrogen electricity generation solutions, right? It's the world is saying that. So it's not just a US problem, it's a world problem. Energy is a worldwide problem. And so we are looking at developing the fundamental tools that are needed to burn hydrogen in gas turbines. If you know the landscape right now, around 40% of the US electricity is generated from gas turbines burning natural gas, and about 25% is from coal, and around 10 to 15% is from nuclear, right? So what they want to do is, natural gas is very clean, but it still produces CO2, which is a greenhouse gas. And so the idea is that we want to mix hydrogen with those turbines and burn them, but that brings up a lot of challenges. And so we are looking at generating experimental data and using using those data to create some simple models that the industry can use to develop the next generation advanced gas turbine solutions, which will be using hydrogen as a fuel. When you burn hydrogen, the only product that ideally comes out is water, and water is also a precious commodity in many parts of the world. So it's a win-win situation from many angles. But the technological challenges with dealing hydrogen are very complex, and so there's a lot of work university level that is needed. And because of this project, we are also funded by Mitsubishi Power, which is an OEM right now, to look at some aspects of the hydrogen turbine. We also got a recent award from Department of Energy to reduce pollution from trucks. So if you look at Class 8 trucks, right, around 73% of the nation's freight is moved by these large trucks, and very difficult to electrify these trucks because they need to run for a long time on the road. And so they are running on currently diesel, and that diesel is not a good fuel when it comes to emissions. And so what DOE is looking at using alternate fuels like renewable fuels, and using them in these tracks. And so we've been fortunate to be part of this new effort, and we'll be working with OEMs and University of Wisconsin on that effort. Here is one area where we are the world leaders, which is supercritical CO2 combustion for power generation. And if you don't know what this is basically burning fuel with oxygen in a CO2 environment at very high pressure. So these kind of gas turbines operate at 300 bar kind of pressure. That is similar to the rocket engine pressures, So you can imagine controlling such an engine and generating electricity. It's very, very challenging. Now, this technology is not just led by the federal government alone. Here is a power plant that is built in this is 50 megawatt thermal power plant built in Texas, and we actually worked with the company called Net Power, who is developing such power to make this solution. So with the supercritical CO2 combustion for electricity, you do not release the CO2 into the environment. You actually capture the CO2. So it's a zero carbon solution. And there are many other benefits in terms of cost and footprint and so on. So here is the latest news that is basically everybody's excited about. Actually, they just delivered electricity to the Texas grid using this technology. So this is a private venture, $150 million invested by Net Power into developing this technology, and we were contacted by them to help with some aspects of this plan. And in this area, we've been funded by several other industries and government agencies, Department of Energy and Navy and so on. And we have published over 25 journal papers in this area. And we are actually from the university level, we are the world leaders in this particular area. Let me talk about some of the ongoing projects in high-speed propulsion and hypersonics and missile defense areas. We work in detonations and trying to understand, so detonation is, something that is exploding. So you can see a detonation versus like a simple flame that is like a candle flame. So such detonation can be used for power generation and propulsion. That's called rotating detonation combustion engines, which can be used for power generation and propulsion. But such detonations are also important from a weapon standpoint, trying to understand, what is in this flow field. Can you make new effective energetics? So those are some of the questions asked by the DoD, and we've been funded by Air Force and AFRL in this area. And so actually my students will be traveling next month in a couple of weeks to AFRL location to make measurements in such an event that you see in this picture. It's a very extremely challenging environment. Trying to understand what's inside there, it's very, very challenging. And so the other project that we have is working with the Navy on solid fuel ramjets for hypersonic propulsion. So here is actually Northrop Grumman's test firing a solid fuel ramjet. So the choice of fuel in such an engine is a STPB, and there are a lot of unknown sort of questions about how STPB burns. And we are actually working with the Naval Air Warfare Center and Naval Research Lab in trying to look at the combustion of solid fuels in our facility. So this is one of the new projects that we started, and it's been funded by ONR. And here is a very interesting project trying to understand the rain droplet impact on hypersonic high-speed flight. And you might think, okay, what is a raindrop doing to a high-speed flight, right? So when you are driving a car, you know that, raindrops are hitting your car, and, it's actually a drag, right? I mean, you have to reduce the speed because you are actually being, the force from the rain is actually causing the vehicle to go slower. Now, when you fly at extremely high speed, that raindrop can actually act like a bullet and actually, damage your vehicle. So trying to understand how does a raindrop affect, when you fly 6 or 7 times the speed of sound, that is very, very important for Department of Defense, with respect to hypersonic weapons. And so here is a comparison of, the force caused by a raindrop as you go up in speed. And so, a small raindrop can be felt equivalent to an elephant hitting you when you are flying that high speed. So what we do is, we study this problem. We have the raindrop, basically water, and we hit that with shock waves and try to understand how the raindrop break up. And this is in collaboration with Mike Kinsel from MAE, and this has been funded by Air Force, our hypersonics program, and we are collaborating with AFRL in that area. This topic I cannot talk much. This is related to rocket and vehicles exhaust plume detection. So you know that rockets, they have this plume, right? Plume is basically the exhaust of the engine, and this plume behavior changes with respect to altitude. And so this is the SpaceX rocket when it is taking off, and here is the same rocket at high altitudes. You can see that whatever is outside this rocket, the behavior of that high temperature exhaust has changed, right? So when you look at an enemy rocket coming towards US, you can take satellite pictures, and that's how you determine what type of vehicle it is, trying to understand the plume, what is in this flow field, and that's how you develop interceptors and try to shoot down those kind of missiles. So we do a lot of work for Army. We've been funded since 2015 in this area, and recently we've been funded by the JSTO and the University Consortium for Applied Hypersonics, which is a consortium of universities managed by Texas A&M. Here is another work that we did for DoD, and this is in counter weapons of mass destruction activity. This has been funded by Defense Threat Reduction Agency. One of the cool things is United Nations is interested in keeping the world peace, and they have an agency called OPCW, and they made a documentary about our research, and it's a very cool video. It's available in YouTube and several other platforms, and it is based on our research, and I am the main actor in that film. So in this work, what we are looking at is, when somebody has a chemical weapon storage, what kind of countermeasures can you use to destroy them? And so typically those kind of storage are in the middle of the city, and in sometimes in bunkers, sometimes in multiple levels below the ground. And so DoD needs to know effectively how to destroy them, and there's a lot of knowledge that needs to be developed how these kind of compounds will be behaving in a high temperature environment. And so we developed the experimental data and developed models, and the DoD is currently using our models to plan their large-scale simulations and missions. Now, talking about space explorations, here are a snapshot of all the space exploration work going in my group. And actually, I'm very proud to say that, we have a lot of undergraduates who work in these companies, but typically, when you graduate with a Ph.D., you are employed in more R&D and design kind of efforts. And so the students who graduate from my group, they are working in all three major space companies. So Andrew is at Blue Origin, Eric is at SpaceX, and Sam is at Boeing Space Program by Merit Talent. And currently we have a project funded by NASA fellowship to Jessica. She's a PhD student. We are looking at developing data that's applicable to new methane and natural gas rockets. And so this is just got awarded. And we have also a project funded by NASA's early stage innovation program, trying to develop power solutions for long duration space missions. So here we are looking at developing alternatives to batteries. When you think about a spacecraft that is going through another planet, and it has to deal with the day and night on that planet. On Earth, and nighttime is 12 hours. But in a remote planet, that 12 hours can be equivalent to 20 Earth days or more, depending on the distance from the sun. So you don't have solar energy for that extended period of time, and you cannot have batteries that can provide such high powered solutions. And there's a trade-off between power, energy density, and weight, and so on. So we are developing this new compounds called pyrolants and associated reactors to do that for future spacecrafts. And we have been funded by FAA and NASA trying to develop LED-based sensors for spacecraft fire detection. So I have many undergraduate students and graduate students who've been supported through that program. So this is from FAA's Commercial Space Transportation Center. So this is, you might think, why FAA is interested in funding something like that. NASA had 60 years of research to develop all the technologies that they needed, right? SpaceX has been around for 20 years and other companies have been around for like 5 years, 3 years. So one of the things that FAA is worried about is, what is the guarantee that these companies will develop safe solutions, when they transport humans to space. And so FAA wants to develop techniques that they can then, industry can adopt. And that's why they are funding universities to develop low-cost fire detectors for space. So here's some more details about the LED project. In the interest of time, I'll just move on to another project that we are doing. So in this project, this is very relevant for the new federal government, trying to understand the atmospheric temperature and humidity and water concentrations around, around clouds. And in order to do this, you have to actually put sensors on high-speed aircraft like jet planes, and fly them through clouds. And so we are developing this sensor, which will be mounted, on the outside of the plane. And basically, the sensor will measure temperature and water mole fractions at extremely high speed, so that they can understand how those properties vary between clouds, and they can update the atmospheric models and correspondingly help them understand global warming and so on. This is one project that I'm not going to talk too much here. This is the DARPA project where we are detecting sensors for opioid detection. So you know that opioid is the #1 killer, overdose killer in the US right now. And unfortunately, these new opioids like fentanyl, it's very hard to detect them and identify them. So people on the field, like law enforcement, they want to know immediately, can they touch a substance that they see, in somebody that's overdosed, right? So you cannot just wait for the lab results to come back 2 weeks later. They need to know an immediate solution, because this is very, very dangerous. And, so law enforcement have died by touching this substance. And so DARPA is funding us to develop a rapid detector, which will be carried by the law enforcement, customs, and military, and they can just point to the substance and see whether it's opioid or something else. And so that is the project goal. In terms of collaborations, I'm always looking for collaborations in the aerospace, defense, and power generation industry. What I want to highlight is the long term. I think in order for us to be the keep our excellence and going forward, we need to target larger programs like multi-university research initiatives or engineering research centers kind of programs. And so those are some of the things that I am targeting. And obviously, all of this research would not have come without the help of my chair, the dean, and the senior research administration within UCF, and also the faculty and staff, especially Office of Research people like Ginny and Matt. And, I deal with them almost on a daily basis. And without their help, I wouldn't be able to, do what I want to do, which is basically train students and, focus on my research. So here are some of the current PhD students. And so currently I have many PhD students, and there's one student with the NSF Graduate Research Fellowship and another one with the NASA Graduate Fellowship. And some of the previous students, so there are 15 PhD students graduated from my group, and they work in industry and government labs, and some of them are in academia. So with that, I stop my presentation, and I'll be Glad to take any questions.